All right. So you all have back your exam number 2. Thoughts? High grade was 100. I want to say the low grade was 11.
That's right.
It's something. Statistics are on Pilot, right? You can pull up statistics, you can look. I am pleased to say that this class did set the bar among the 4 lecture sections. This is good. You did not set the bar on the first exam. That was Josh's class. You know, and I just said, well, he's just got better students than I do. Clearly, can't be the teaching. And so, but anyways, you know, regardless, I was proud of you guys. Performance was pretty good. I mean, it's, you know, I didn't think the exam was overly hard. We have one student that had a medical issue that's started taking it right before I worked in here. So I'm gonna post the solution as soon as I'm out of here. So you can take a look at the solutions, right, and compare them to the prior posted exams. I don't know. I mean, overall, some of it I thought was kind of softball. The last problem was the same bead problem from last year flipped upside down, right? Everything's got a negative side. I mean, geez, that's the softest beam problem I've ever thrown on an exam. So I thought that was, you know, I thought the one with the derivative that had the exponential in front of the sinusoid, we've done that kind of function before several times on the second exam. So, you know, but that's on the upper level of kind of hardness. So that one was harder than typical. The last problem was easier than typical. The ones in between I thought were about the same. I heard some feedback that people didn't like the numbers on the matrix algebra problem. I mean, I don't know. You just divide the whole thing by 1,000 and deal with single digits. But even if you carried through all the numbers, I think Josh's solution, I think he carried through all the big numbers step by step. Wasn't intended to be problematic. It was just intended to be a typical example of the kind of numbers you got to deal with. So. Anyways, besides that, I thought it was a fair exam. Again, high grade was 100. Okay, so nobody can say it wasn't completely doable. But as always, overall performance typically degrades, right, from the first to the second exam. The material's harder. There's a lot more information on there that's not just review from pre-calculus and trig. So if you'd never had calculus before, and even if you had, you know, the topics in sinusoids and matrix algebra is kind of new for people, and the sketching problems tend to be kind of new for people. So you had to be well prepared. But even so, overall, I want to say, geez, this group right here, 90 of you guys, I think the average was like in the mid 70s, and I think the median was like a 78 or something. So not unhappy with that on a second exam. Overall, one of our lecture sections really did pretty poorly compared to the other ones, so it brought the overall average down further. But bottom line, distribution kind of typical. A lot of people did well. Just about half you guys got an A or a B. I was happy to see that. So I'll post the solutions. Download the solutions, right? Look at your grading. If you don't understand your grading, double check your points for sure, right? It's up to you to make sure the grade on the front reflects the grades that were actually given. Double check the math on the person that tallied and entered it. Make sure we got the right grade entered for you. If you see any problems with the grading or whatever, okay, then you let me know about it, and then I will sift it down back to the people that graded those particular problems if we need further consideration. But again, the way that you would want to do that is if you look at the posted solutions and you say, well, geez, I've got that. You know, why did I lose -3? You know, something like that. It's possible. A grader misses something. You know, if it's a judgment kind of decision, your odds of getting points back by quibbling are not high. Okay, but the other one is to double check for each problem. They got -1, -2, whatever. Double check the individual tallies on all your problems to make sure you're getting the grade that you actually earned. Okay. All right, so exam number 2 is behind us. Again, implications of exams. If you got a 50% on this exam, that, you know, the implication is it costs you a letter grade in the course. It's worth 20% of the grade. So a 50% would be 10% of your final grade gone. Okay, which is not the end of the world unless you do that on all the exams, right? If you do that on all the exams, then you're down to all the way down to the bottom of a C if everything else is right. Okay, so if you do that repeatedly all 3 exams, you're probably gonna have to retake the class because you need a C or better right, to kind of move on in your program. So, so again, if you had a bad day, same story as last time. Assess why you did the way you did. Okay, anybody that got a very high grade on this class, I think we're past the point, or in this exam, we're past the point of the resting on the laurels. So anybody that got mid to high 90s on this, just prepare the same way for the final, and you know what you're doing. Okay, people that felt like they could have got a higher grade than what they actually got, just go back and make an assessment about, is there something you can do differently when you prepare for the next exam? Right? Or did you really feel like I've prepared, everything they said, I went to the reviews, I worked all the exams, whatever, I still got an 81. At some point, differences between A's and B's come down to execution during an exam. It happens, okay? But keep in mind, a B's a decent grade. All right, I would argue anybody that got a C or lower on any of our exams can identify places where they can change in order to improve on the next exam. Okay, and by the way, I've seen some inspirational stories. I've seen students in this class, academically dismissed from prior institutions, failing out of community college, showing up here at some point, getting low C's on both the exams, like 71, 72, having had worked for hours and hours and gone through the reviews and did everything I said and still got a 71. All right, the student I'm thinking of right now, aced the final exam. 100%, okay? Pulled out a B in the class. So nothing is impossible. You've got the rest of the term to say, here's the grade that I'm headed for. Here's the grade I actually want. What am I going to do about it? Okay? So ball's in your court, guys. I want everybody in here to get an A or a B, even though I know it won't happen. That's what I want. Okay? So with that, is it true that Dr. Rattan, when he came in, got all the way through the dynamics lecture notes? This is my understanding. Yes. And as I had said ahead of time, right, we kind of hit the conceptual peak in this class, I believe, when we did integrals in statics, right? And we were doing centroids and distributed loads and those things. That was pretty, heavy conceptual stuff. I feel like dynamics is now over the hump and back on the way down. You guys agree with that? All right, the same kind of stuff we did in derivatives, but just now the derivatives are backwards and we can do more things to do the sketching. Okay, when we get into the differential equations point of the class here, I will post old final exams just like the midterm. Okay, and what you'll see when we post the old finals is that you're going to see the same kind of sketching problems again. Right? So if you didn't like the sketching, you'll see them on the final, but now you got more power available. Right? Not just derivatives that tell you about slopes. Now you got integrals that tell you about areas. Right? And when you work those problems on the final exam, it's, hey, use calculus. Right? And it's redundant information. If you use derivatives and integrals, you can double check your understanding of these problems. So be thinking ahead about that. If that was your weakness, thinking about how you can use what we've done with integrals to improve your ability to sketch functions that maybe don't come with an equation. We're going to see more of that starting today when we move ahead with applications and circuits. All right, so with that, oh, that's a great question. Did I even pass it around is the real question. Here it is. Thank you. Okay. Sign-in sheet is going around. All right, so application of integrals in electric circuits. So by this point, we've kind of got the basic physics out, right, for circuits. We deal with things like resistors and inductors and capacitors, and the inductors and capacitors are the ones that have the derivative kind of relationships. So when we look at integrals, we're going to be looking back at some of those same circuit elements, okay, and, so this is integrals in circuits. Okay, and again, we're talking about EE 2010 is the course. Okay, and so first example I want to look at is current, voltage, and energy in a capacitor. And we'll talk about it in kind of a generic way first, and then we'll put some numbers in. Okay, so this is going to be current, voltage, okay, and energy, okay, stored in a capacitor. Okay, and so here's what we're talking about. I will have a circuit that has a current source that I'm going to write as I of t, okay, and it's just charging up a capacitor. Okay, so there's my capacitor, and then what I'm going to do is go ahead and measure the voltage across the capacitor out here. So I'll have an output voltage plus or minus. This is going to be my voltage here, V of t. Okay, and so here's my capacitor right here. We'll call it C. Okay, and here's the question. For t greater than or equal to 0, okay, I'm going to start up this current source. Okay, I of t is going to be equal to 24 e to the minus 40t. Okay, and the units on this guy are going to be milliamps. Okay, so given the initial conditions, V of 0 equals 0. Okay, the voltage at time t equals 0 is 0. Okay, what I want to do is find the following. I want the voltage, V is a function of time. We'll call that part A. And then part B, we'd like to get the stored energy. Okay, and we're going to call that W of t. Okay, so we'll have to kind of recap, how do I go from a current in a capacitor to an idea of voltage and then also stored energy? Not going after it. Okay, so does anybody remember what's the derivative relationship for voltage and current in a capacitor? Just saw some of this on the exam. I equals, right? It's a dV dt, but there's something else in there. C dV dt, right? So the capacitor is in there. Okay, so you want to recall the relationship, this guy. Right, in a capacitor, I've got I of t is equal to C times dV dt. So what I'd like to do is think about how can we go from that and in general solve for the voltage given a current. Okay, and so, well, if that's true, then if I'm trying to solve for the voltage here, I got to isolate the voltage part of this equation. So let me flip it around and say then wouldn't dV dt be equal to 1 over C times the current, I of t, right, if I just solve for dV dt. So that is a statement that we used, right, on the second exam to think about how I can sketch voltage, right, or how I can sketch current, knowing, right, that the current is the slope of the voltage. Okay. So in this case, if I'm given the current and I want to solve for the voltage, okay, what I'm going to want to do is integrate both sides, just like when we did dynamics. Dr. Rattan did dynamics, right, and talked about if I'm given, you know, velocity, dx dt, I can integrate that to get position, x of t. Okay, and so that's what we'll do, right? So integrating both sides of the equation, I will integrate on the left dV dt dt, and I'll do it, you know, between the initial condition 0 and any time t, right? So it's like a definite integral where the top limit is a variable. Okay, and on the right, I'll have to do the same thing. Integrate from 0 to t. I've got 1 over c of I of t dt. So given that integration and derivatives, right, differentiation, are inverse operations, what do I get when I take the integral of the derivative of something? I get the something, right? So if I take the integral of the derivative of the voltage, what do I get? I get the voltage. Okay, so on the left side, I get the voltage, and don't forget, you got to put the limits on here, 0 to t. Okay, and on the right side, well, I'd need to have an equation here. I guess what I can do is I could put 1 over c out front, because that's a constant. Okay, but then I've got this guy, the integral from 0 to t, right, of I of t dt. So then if we move on now and we evaluate the limits, okay, then on the left, I'm going to get v of t, that's the top limit, minus the bottom limit, v of 0. Okay, and on the right, I'll have still the same thing, 1 over c, the integral from 0 to t of I of t dt. So you can see here, this is the way the initial voltage comes into the equation, okay, just like in a position, velocity, acceleration problem. If I want position, I've got to have initial values of things like velocity, right, and position potentially, in order to get an answer. Okay, so finally, if I just solve for the v of t, I'll get an answer that'll work no matter what my current is. V of t is always going to be my initial condition, v of 0, that's what I start with, right, plus I'll have 1 over c, and I'll need the integral from 0 to t of the current, I of t dt. So you put a box around that and think about that as a general answer, no matter what the problem statement is for the initial condition and for the current. I ought to be able to just evaluate this integral, add the initial condition, and I'll have the voltage at any time t. Questions on the plan here before I move forward? All right, so again, all we're doing is derivative backwards. All right, so given this, let's go ahead and start with the numbers that we have. Okay, so in this case, what do I know about the initial? V of 0 is what? 0. Okay, so right away that first term is gone, right? And I've got values, you know, for the rest of this, right? And so did I give C a value? Nah, I should do that. Okay, so let's say that the C is equal to, what do we say? 3 microfarads. 3 microfarads, okay, given in the circuit. Okay, so V of 0 is 0. I know what the C is. C is 3. What does a microfarad mean? 10 to the minus 6. So 10 to the minus 6 farads. Okay, and then I also have an answer for I of t, right, given in the problem. Okay, and that was the 24 e to the minus 40t milliamps. In general, when I start messing with milliamps and microfarads and whatever else, I probably should think about putting things in the base units and just let the numbers take care of themselves. So 24 milliamps, if I want to stick with base units, I can write this as 0.024, right? The milliamps is 10 to the minus 3. Move the decimal over 3, you get 0.024 e to the minus 40t, and the units are amps. So what I want to do is plug those numbers in, right, and find the voltage V of t. All right, questions before I move forward? All right, so here we go. So V of t is equal to V of 0. V of 0 is 0. Plus, I got 1 over c, so that's 1 over 3 times 10 to the minus 6, okay, times the integral from 0 to t of I of t dt. So this is 0.024, right, and I've got e to the minus 40t, okay, dt. So what can I do with that 0.024? I can pull it out front, right? I got a constant inside the integral, so I can pull the 0.024 right out the front. So V of t is going to be 0 plus, if you pull the 0.024 out, right, you'd have 0.024 divided by 3 times 10 to the minus 6 times the integral now from 0 to t of e to the minus 40t dt. So what's 0.024 divided by 3e minus 6? Somebody want to run that? Do it in your head if you're good with decimal points. 3 goes into 24 8 times. I got an e minus 3 up top, a minus 6 in the bottom. Gives me a plus 3, right? 8,000? Seems about right. When in doubt, use your calculator, that's fine. Okay, 8,000, and now I got to work this integral. So e to the minus 40t. Is that something that's on the sheet? Yeah. Sure. All right, it's like an e to the st. Anybody remember, how do I integrate an e to an st? Close. If I take the derivative, yeah, it's a 1 over, right? I've got to divide by the s. So in this case, the s is the minus 40. Again, when in doubt, just take the derivative. Okay, so we'll put the bracket. It's minus 1 over 40. That's 1 over the exponent. And then the same thing, e to the minus 40t. Again, we will see this a lot when we do differential equations, but the fact that the integral of an exponential function is the same exponential function, right? And the fact that the derivative of an exponential function is the same exponential function, the only difference is a constant, that gives us an entire strategy for solving differential equations. Okay, so we're going to see this again in a couple of weeks. Not even a couple of weeks. Next week, right? Okay, so I got to put the limits on here, right? 0 to any time t. So I got a couple choices. I could plug the limits in, everything in the brackets, but anytime you have a constant inside the brackets, right, it's going to be the top minus the bottom. So what can I do with the constant here? I pull it out, make my life a little easier. So v of t, I'm going to write this as pull out the minus 1 over 40. So it's minus 8,000 divided by 40 right here. Okay, and then when I evaluate these limits, I'm going to get, right, I just have the e to the minus 40t. So the top limit, e to the minus 40t, minus the bottom limit, e to the 0. Is e to the 0, 0?
No, it's 1.
It is 1. Okay, now this is a really important point. Okay, electric circuit problems are the biggest kind of problems where if you get into this rut of I'm just not going to worry about the 0, you know, you're missing like all of the magnitude, right? This number, e to the minus 40t. As I start to march out in time, what happens to this thing? Yeah, so I mean this thing dies out quickly, right? This is the number 1, right? This number is a lot smaller than that number. Okay, so you don't want to be missing the stuff that tells you what's going on, right, in the steady state. Okay, all right, very good. So 8,000 divided by 40, negative 200. I get v of t is equal to minus 200. Okay, and this is going to be e to the minus 40t minus 1. Okay, and you could write that a number of different ways. You might want to distribute through the negative sign, or you could write it as two different terms. Okay, so I'll write it this way. V of t is equal to, if I distribute that through, I'll get a positive 200 minus a 200 e to the minus 40t. What are the units on that? Yeah, this is volts. Okay, I'm going to write the word out since my V over here already looks like a V. Questions? It's a pretty straightforward, right? I've got the current. I've got a derivative relationship between current and voltage. So I just integrate the equation, right, and go the other way in order to get the voltage. Yes?
Shouldn't the 200 minus, shouldn't that be switched instead of like that?
Well, so if I distribute this through, I did kind of more than one step. The first term would be minus 200 e to the minus 40t. That's the second term here. Okay. The second term is minus times minus is plus. Okay. Again, I will tend to do things in here, particularly at this point in the class, the way I would do it myself, which sometimes involves a couple steps of algebra at once. If you don't follow the algebra I did, you need to do exactly what he just did, which is say, can you back up the cart and explain that? Okay, because the devil's in the details. You're going to get the right answer. You got to be able to execute the algebra. So if this takes you 2 lines of algebra to get to there, that's fine. Okay, write down what you need to write down. Are we good? Okay, good. So I've got voltage. All right, so now, what was part B? It said find the energy. Okay, so how am I going to get the energy? So got to go through a little bit of a step here. Okay, so this was find W of t, right, which is the stored energy. Okay, and so how do you think I'd get stored energy? Say again? Okay, so how does power compare to energy? All right, so I'm getting somewhere because I got voltage here, and I started with current, which is somewhere here. All right, so I've got current right here and voltage, so I can definitely get power. If I had power, how could I get energy? What's the units on power? Watts. Go ahead.
Joule per second.
Yeah, it's a joule per second. What's a joule? Joule is the energy. Okay. Again, physics isn't a prereq for this, right? So if you haven't had this besides in here, right? Just pull out the cobwebs. We talked about this a little bit earlier. Okay. Power is voltage times current, right? It is the rate of change of the energy. So I've got a derivative relationship by definition, right? And so you want to recall this guy, right? That power by definition, P of t, is dW dt. Okay? In other words, this is energy per unit time. Okay? And so I've got a derivative relationship there. I know I can get the power because I got the voltage and I've got the current. All right, so I'll have an equation for power. So apparently, I ought to be able to solve for the W from this. So if you flip it around, dW dt is equal to the power. How do I get W? Not just multiply by dt, right? But integrate both sides with respect to time. Okay, but you know, if you want to rationalize the math like he said, sure, multiply this side by dt, multiply that side by dt, and then put an integral side here and here, right? An equation means I can do whatever I want on the left as long as I do it on the right. Okay, so we're just going to integrate both sides of the equation, okay, and see what we get. So on the left, the integral from 0 to t of dW dt dt is going to be the integral from 0 to t of the power P of t dt. So, going to have to evaluate the integral over there on the left. When I integrate dW dt, what will I get? Yep, when you integrate the derivative of anything, what do you get? You get the thing, right? So I'm integrating the derivative of W. So on the left, I'm going to get W. W of t, evaluated the two limits between 0 and t. And on the right, I still have the same thing, integral 0 to t of the power P of t dt. And so if I evaluate the limits, okay, I will get the top limit, W of t, minus the bottom limit, W of 0. Okay, and this is going to be equal to the integral from 0 to t of P of t dt. So W of t then is going to be the starting point, W of 0, plus the integral 0 to t of the power P of t dt. Okay, and so this guy looks an awful lot like what we just had for voltage, except this is now a general formula that will work for stored energy. All right, so what do we got? W of 0, initial energy. If I start out over here, right, what's the voltage across the capacitor at time t equals 0? This is 200. Put a 0 here and you get 1. 200 minus 200, 0. Remember, that was an initial condition. Okay, so it's a statement that the capacitor is initially discharged, right? There's nothing on it. So if it's discharged, I've got nothing on it, then how much energy do I have stored? Yeah, it's my starting point. Okay, so here, W of 0 equals 0, right? And this thing is initially discharged, right? So no stored energy in the capacitor. Okay, and great. So basically all I have to do is integrate the power. Okay, and so I want to recall what the power is. Yeah, P of t is, if I've got voltage and current, multiply them together. V of t multiplied by I of t. Okay, and so in this case, right, what was my I of t? It was this guy, right? 0.024 e to the minus 40t. And I've got the voltage V of t. So apparently the power that I want to integrate is going to be this guy. It's the voltage, 200 minus 200 e to the minus 40t. All right, that's the answer we got for the voltage, multiplied by the current, 0.024 e to the minus 40t. So that is the power function that I'm going to have to integrate. Questions? Okay, so before we forget, this is the 0.024 e to the minus 40t, all right, amps. Okay.
ITUE, what does that mean?
I'm sorry?
ITUE.
IT, show me where.
Over there.
Probably just can't read my chicken scratch. Here?
It's not there.
Or? Find?
No. It's on
Recall?
the other side of the board.
Here?
Yes.
Here. That says here. That's hieroglyphics for here. Okay? Are you guys good? Everybody with me? Very good. Yeah, I like to say, you know, that when I was starting school, I was like exceptionally good at handwriting when I was in 2nd grade. So that's when I stopped working on it. Okay? This is what's left. Excellent. Okay, so moving on, I want to get W of t. Right? So W of t, we already concluded W of 0 was 0. So I'll say 0 plus the integral from 0 to t, and I got to put that power in there now. Okay, and so the power, right, is going to be, you know, that, which hopefully I can simplify some. So 200 minus 200 e to the minus 40t, right, multiplied by the current, 0.024 e to the minus 40t dt. Yeah, I mean, so the way that that looks, I think the safest bet is can we just distribute this thing out and just get a, you know, a couple of terms here instead of one. Okay, and so let's do that. Let's take this term times each of these, okay, and see if we can simplify the numbers a little bit. So the zeros here, integral from 0 to t. I've got the 200 times 0.024. So I'll just write that out to be clear. 200 times 0.024 e to the minus 40t. That's distributing to the first term, right? Minus the same thing. I'll have the 200 times, right, e to the minus 40t. That's the second term times the 0.024 e to the minus 40t dt. So what am I going to get? 200 times 0.024. Somebody want to run that number for me? Yeah, W of t, I'll get the integral from 0 to t, so this isn't too bad. The first term is just 4.8 e to the minus 40t. And then I got the next term, right, which is, boy, it's the same number again, right? 200 times 0.024 is still going to give me 4.8. What's e to the minus 40t multiplied by e to the minus 40t? Yeah, you add the exponents, right? Same base over here. So 40 and 40 gives me 80. I'll get e to the minus 80t. So can I do anything with this? I got e to the minus 40t here. I got e to the minus 80t there. Can I add these two up? Right. I mean, it's like trying to add x cubed to x squared, right? Doesn't add up. Okay, so I'm stuck with two terms. I do have a 4.8 in each term. I suppose I could pull that whole thing out if I wanted to do that. Either way. Okay, and so I got to integrate this whole thing with respect to time. Okay, so two terms, it basically means I got to do the integrals one term at a time. Yes?
Could you pull out e to the minus 40t in each term?
Yeah, see, I could do that, right? And if I did that, I would have a constant, right? So it would be a 1 minus. But then in order to do the integration, I'm really kind of stuck, right? I mean, because these are two separate terms, yeah, I mean, I could write it as e to the minus 40t, right, and factor it out, okay? But it's not going to help me when I go back to do the integral. Okay, so I think the best strategy for doing the integration here is to just one term at a time, evaluate the limits, and go. Other questions? Concerns? All right, so let's give this a whirl. One term at a time. When I integrate the first term, okay, what we'll do, because there's two terms that are different exponents, we'll do the limits. We're going to do them like they're two separate integrals. Okay, so we'll do the first term with the limits minus the second term with the limits. So the first term here, when I integrate this, the 4.8 goes where? Out front, 4.8. And so then I get the result of the integral. When I integrate e to the minus 40t, I get what? Yeah, same as the last integral we had worked. I get the minus 1 over 40, e to the minus 40t. Right? So if I'm on the final exam and I stop at this point and I get confused and I think, wait, did I do this right? How can I check and make sure? Take the derivative. Okay, take the derivative. The minus 40 comes down, cancels the front. Right? E to the minus 40t, I'm back up to here. Okay, so you can always go back a step with the derivative and put the limits on, 0 to t. And then I got the next term, right, which is minus. I got the 4.8. And then I've got the result if I integrate e to the minus 80t. Yeah, now it's a minus 1 over 80 e to the minus 80t. And I got the limits 0 to t. Okay, so this is one where you got to be, you got to be kind of anal with your negative signs here to make sure you don't mess this up. Okay, probably the cleanest way to deal with this is to pull the constant out of the brackets, right, and then evaluate the limits. Okay, and again, there's more than one way to manipulate the algebra, but I think that's the cleanest thing because when you evaluate the limits, it's the top limit minus the bottom. If you have a constant that's got a minus in it, you've got a potential to mess up the double negative. So I would pull the whole thing out myself. So write this as minus 4.8 divided by 40 out front. And if I do that and I evaluate the limits here, the top limit is e to the minus 40t. The bottom limit gives me what? Yeah, it's going to be 1, right? E to the 0, which is 1. Now over here, look what happens. I'll get minus 4.8, but I pull out the minus 1 over 80. Yeah, so this is going to be now plus, right? 4.8 divided by 80. Right? And then again, now it's top limit minus bottom. E to the minus 80t minus e to the 0, which is 1. Okay, so now we're getting somewhere. Okay, and so finally, when you're done here, you can simplify this a little bit. Right? I'm not going to be able to add the 40t and the 80t, but I've got a constant term on each one of these things. Okay, and so what will I get? E to the minus 40t, right? I've got this guy right here. 4.8 divided by 40 gives me what? Yeah, right? 4 goes into 48 12 times. Move the decimal. Minus 0.120 e to the minus 40t. That's the first term. Then I've got the same number minus negative gives me a plus 0.120. Okay, so just multiplying through the first term. Second term, if 4.8 over 40 is 0.12, then 4.8 over 80 is what? Yeah, half of that, right? So 0.06. So I'll get plus 0.06 e to the minus 80t And then I've got the same constant here. That one's going to be negative, actually. So this is minus 0.06. Okay, so this is all W of t. Just ran out of some board. So finally, it looks like I can get this down to 3 terms, right? Because I got a 40t, an 80t, and the constants I can add together, and I'll get what? 0.12 minus 0.06 is going to be another 0.06, right? Positive. So combine these 2 terms, and I'm just going to go ahead and start here with the positive term. Okay, so the positive one is the 0.06. 0.06 e to the minus 80t minus the 0.120 e to the minus 40t, and then finally plus 0.06. What are the units on this? Yeah, this is energy, so we'll put a big J at the end. Okay, so there it is. Questions? All right, so the point is, right, and I can do the same thing with an inductor problem, right? In an inductor, this guy over here, right, the governing law is what? I of t is C dV dt, right? And an inductor, the relationship's the other way, right? V of t is L di dt. So either one of these types of problems, I can start with one, integrate both sides to get the other. Okay. Derivatives backwards. All right, let me take a look then at an inductor problem that does not have an equation. Okay, and essentially going back to the same kind of problem we looked at when we did derivatives. Okay, and as I warned, more of this kind of sketching on the final exam. So let's think about this case again of current and voltage in an inductor where I'm going to take a 9-volt battery and keep switching the terminals. So current and voltage in an inductor. So let's say I got a direct voltage source, V of t right here, okay, and an inductor right here. Okay, and let's say in this case, I'll use L is equal to 500 millihenries. Okay, and I know that I'll have a current, I of t, going around. Okay, and what I'm going to do is go back and forth on the terminals, right? And we're going to say that this voltage over here is actually a 9-volt battery, right? So this is V of t in volts. Okay, and so we're going to alternate this thing between 0, and then we'll have plus 9 volts. Okay, and then down here we'll have minus 9 volts. And I'm going to do this for 8 seconds. So 2, 4, 6, 8. So this is just t right here in straight up seconds, not milliseconds. Okay, and so here's how it'll look. For the first 2 seconds, I'm just going to keep the positive connection. And then after 2 seconds, I'm going to switch the terminals, and I'll have the negative voltage. Okay, and then I'm going to repeat the cycle. Okay, so 2 more seconds positive, and then straight back down again, 2 more seconds negative. Okay, and this is what we call, by the way, what kind of wave? Yeah, this is a square wave. Okay, so I can apply a square wave again with a direct current by just, or direct voltage by just switching the terminals. All right, so what I would like to do is, given the voltage current relationship, okay, for an inductor, can I take that voltage curve and use it to sketch the current curve? The answer should be yes. Okay, and in fact, this is a problem that I can do using derivatives we already know. Okay, so here's the idea. Knowing V of t is equal to L times di dt, the voltage current relationship, okay, can I plot, right, I of t, but we're going to do it this time using integrals. Okay, so this is a problem where I can do it either way. I can use the idea of slopes like we talked about a couple weeks back. Or I could say no, I can just use the entire idea of integrals to do the same problem. As opposed to slopes, we'd be talking about what then? Derivatives are the slopes. So derivatives gives me a slope. What does an integral give me? Areas. Can I use areas, right? And a general idea of antiderivatives. Okay, and the answer is yes, right? And we'll see before the end of these lecture notes, I don't know if we'll get today, probably go into next time, but we'll see that there are certain problems where you need to use both. You need some slope information, you need some area information. That's where most of the power is. This is one where we know we can do this with slopes. So let's see whether or not we can do it with areas. Okay, so let me talk about this in a general way first, then we'll go back and do this problem. Okay, and so in general, this says solution. Okay, if I start with this relationship, then I can solve for current. di dt would be 1 over L times the voltage, V of t. So if I have the derivative of current on the left, right, and I want to find the current, then I should do what? Integrate. Right? So if I integrate the left side from 0 to t, di dt dt, that would be the integral from 0 to t of 1 over L times V of t dt. And on the left side, when I integrate the derivative of the current, what do I get? I get the current. So this is going to be I of t evaluated between 0 and t. Okay, and on the right, can I do anything with that 1 over L? I can pull that out, 1 over L, integral 0 to t of the voltage, V of t dt. And so when I evaluate the limits on the left, I'm going to get I of t minus I of 0, my initial current, okay, is equal to 1 over L, right, integral from 0 to t of V of t dt. Okay, and so this will give me something similar, right, to what we just looked at for the capacitor. As long as I have an initial value of the current, I could say that I of t is always just going to be I of 0. Right, it's going to be I of 0 plus 1 over L, and then I will integrate the voltage, 0 to t, V of t dt. Okay, so that is true for the I of t at any time, okay, right here. Okay, and so for this problem, that'll give me an equation for I of t. But if I want to think about this maybe in terms of areas instead, then what if I went, instead of between 0 and any time, what if I just went, say, like between t equals 4 and t equals 6? Right? Or between any two times, right? Time t1 and t2, no matter what they are. Okay, if I did that, okay, I could make this argument between any two times t1 and t2. All that would do to this argument is change these limits, right? From t1 to t2, and I'd have a t1 to t2 here. So what I would get is the change in the current, I2 minus I1, right? I2 is the current at t2, I1 is the current at t1. Okay, and that would be 1 over L times the integral from t1 to t2 of V of t dt. So the way to think about this is the left side of this equation, okay, represents the change in the actual value of the current. All right, so this is the change in I of t, okay, and that change occurs from time t1 to time t2. On the right-hand side, I got a couple of things. I got a 1 over L. I'm going to scale it. Okay, but then what about this guy? What does the integral of V of t dt between any two times represent? It's the area, right? No matter what 2 times I talk about, when I do that integral, right, I would get the area under the curve. Okay, so this guy here is the area under v of t between those 2 times, right? Or from t1 to t2. Okay, so apparently, if I want to get actual numbers on the graph, all right, then as long as I know where I left off, right, like say I know I1, I could use a relationship like this to get I2. All right, if I know I1, then the change across the interval, I can just come and look at the graph of this one, compute the area, which in general won't require an integral to be actually evaluated, right? Because those are rectangles, yeah, squares. I can find the area, all right? And then I can scale it by 1 over L. I need the L number, and then I'll have an answer. So that's going to be the plan moving forward. Questions? All right, so back to this. What I would argue is we ought to be able to come over here and look at this in each interval. Okay, and by the way, if I can do this for the first 4 seconds, do I have a lot more work to do the next 4 seconds? No, it's a periodic function, right? And so really, I got to think about doing this for 1 cycle, and then this thing is going to repeat itself. Okay, so here's the way I'd like to think about it. Let's do a whole period, and let's deal with intervals where it's obvious what I can calculate here. All right, so the first interval, I know what v of t is for the first 2 seconds. So if I go 0 less than or equal to t less than or equal to 2, right, and of course units there is seconds, write down what you know. What's v of t equal to? 9. It's equal to 9. What kind of function is 9? It's a constant, right? Again, this is important. It's not just the value at a specific time. It's 9 for the entire interval, right? So it is a constant function over that time. So this is constant. Okay, and so if that thing's a constant, and I know that I of t is 1 over L, right? I of t as a function is 1 over L times the antiderivative of v of t dt. Then it means that if v of t is a constant, to get the kind of function I'm going to get for I, I'm going to have to integrate v. Yeah, so what kind of function do you get when you integrate a constant? You get a line, right? It's like a t to the 0. It's now t to the 1 divided by 1. Okay, so this guy now will be linear. Note that we made the same argument using the idea of slopes before. Now we're using the idea of an antiderivative, right? Derivative backwards gives me the same conclusion. I of t has to be a line. So here's the thing. Okay, we got to have a starting point, so I probably should have said that. Right? So given I of 0, right, as a starting point, we're starting off with no initial current. Okay, I ought to be able to figure out what the endpoint is. Okay, and that's how I'll use this business here. So if I know the starting point, right, is 0, then I can get the answer at 2 seconds because I2 minus I0, in other words, the change in the current between those 2 points, okay, is apparently, right, this statement over here is 1 over L, and I'll need the integral from 0 to 2 of v of t dt. So again, I of 0 is 0, so I2 minus 0, 1 over L, we can put in the number, 500 millihenries. What is that in henries? 0.5, right? So I'll write it as 0.500. Again, when in doubt, just use base units and everything works out nice. So 1 over 0.5, right? And now I want to evaluate this integral. I got a couple of choices. I can put the function in. It's not a complicated function, it's 9, right? I can integrate 9. But I would really rather at this point that you say, look, I mean, isn't just this box right here, isn't this the integral from 0 to 2 of v of t dt? Sure. All right, so again, biggest power of calculus is knowing when you don't actually need to use it, right? In other words, not actually working out an integral. If I know it's the area and I can see what the area is, then I'm going to get what here? 18, right? I'll write it out. It's the base, 2, times the height, which is 9. Okay? And so that's the area under the curve. So 1 over 0.5 is what? That's 2. Okay, so then according to this is going to give me an answer for I2. 18 divided by 0.5 is what? 18 times 2? 36 amps. Okay. So here's the thing. I haven't used a concept of a slope or a derivative here, right? I used a concept of an antiderivative to figure out what kind of function it's going to be. Once I know it's a line, how many points do I need to draw a line? I need 2 points to draw a line, right? And I got a starting point, which is 0. I got an ending point, which is 36. Can draw the line, right? So we'll come over here for that. So if I want to come over here and plot the I of t now. All right, so this will be I of t over here in amps. Okay, and I know I got to have a 36 on there, so here's 0. Maybe put a couple tick marks, 18, 36 like that. And I got to go out here for 8 seconds. All right, 2, 4, 6, 8. T over here in seconds. Okay, then what I know is I'm going to start over here at 0. And after 2 seconds, I'm going to be up here at 36. All right, and so it's a line. I connect the dots. Questions? By the way, what's the slope of that line? Is it 9?
No,
It's 18, right?
Yeah,
Over 2 up 36. So, you know, I didn't use the slope to sketch the line. I used the area to draw the line, and then I calculated the slope, right? And boy, what's the statement about the slope? You know, isn't the slope supposed to be, isn't di dt supposed to be 1 over L, right, times the voltage? L is equal to what? This is 1 over 0.5, right? So, you know, this is the same problem we did back in derivatives, right? The slope of the current for this problem is twice the voltage. What's the voltage? 9. What's the slope? 18. Okay, that right there, that's the fundamental theorem of calculus. That's what that is, right? I mean, I didn't use the slope to get this. I used the area to get that. And then when I go back and I look at the slope, it's like magic, right? There it is. Okay, the relationship between derivatives and integrals, that is the fundamental theorem of calculus. Questions? All right, so I'm halfway there, right? Because we said if I can just get through one interval, then I would have a periodic function. I could, you know, go from there. So let's take a look at the next interval, 2 to 4. So 2 less than or equal to t less than or equal to 4 seconds. What is it that I know? V of t equals what in that interval? -9. What kind of function is -9? It is a constant function, right? So the voltage is constant. And to go from voltage to current, I know that I of t all right, is going to be 1 over the L, all right, times the antiderivative of the voltage. So if I stick a constant in there and I integrate it, I get what? Same idea, right? Another linear function, straight line. Great, so I know I of t is another line. Okay, do I know the starting point? Yeah, I mean, it's where I left off, right? Here's the starting point. So apparently, all I need is the ending point, and I'll be golden. So in order to get the value of the endpoint, right, this is what the integrals do for you. The areas under the curve give me actual numbers, right? Numbers for the values. So I can say now that I4 minus I2, the change in the I over the interval 2 to 4, right, is going to be 1 over L times the integral from 2 to the 4 of v of t dt. So let's write this in here. I4, I don't know what it is, minus I2, do I know I2? Minus 36 equals 1 over L, do I know that? L is? 0.5. All right, so it's 1 over 0.5, so it'll be 2 times this area right here. So I could stick the minus 9 in, all right, and do the value, all right, or I could just come over here and look at this box and say, isn't this box right here the integral from 2 to 4 of v of t dt? And that box would be what? Base times the height? So the base is how much? Area of the rectangle, the base is still 2. What's the height of that rectangle? Negative, right? Remember, for the purposes of calculus, areas can be positive or negative. Below the surface, right, below the axis is negative. So it's 2, right, wide, and it's minus 9 tall. Okay, so now I'm going to get I4, right, is what? 36, I move to the other side right here, right, plus 2 times 4 minus 9. Yeah, plus negative 36. 36 plus negative 36, 0. So apparently, I know what type of function it is, right? It's a straight line. A little far here. Okay, it's a straight line, and I know where it ends and where it starts, right? So I just connect the dots, right? And so right here is my I2. This is my I4, back down to 0. So now I'm back to 0 current, and I'm right here on the waveform, okay? And so I'm just starting the whole problem over again. All right, so at this point, I can just realize that when I take a square wave for voltage across an inductor, then I get what kind of wave for current? Yeah, this is my triangle wave now, right? Okay, and that's it. So I know I6 will be right there, okay, and this will be I8 over here. Okay, and so this is my triangle wave. Questions on that? All right, so I want to make one more point. Okay, and that one is, you know, as much as I love the idea of coming in here and looking at the box and just calculating the area of the box, there could be times, like say I'm going to write an algorithm to control this thing automatically, I want to use the areas. Okay, there could be times where I actually would like to know the equation. Okay, and so again, doing this by looking at geometry that I can do without calculus, you know, can I use the calculus, actually do an integral to figure out the equation of, like, you know, this line right here? What's the equation for I of t between, say, 2 and 4 seconds? You know, how would I get that? Okay, and I ought to be able to do it, right? Let's think about it. So this is just an aside, right? That answer is done if all I want to do is plot this thing. So how do you use the integrals to get the equation? Okay. So I'm just going to call this a note. Okay. You can use the integrals to find the equation for I of t. In any one of these intervals that you want, okay, in any interval. So let's just do one, for example. Okay, let's take a look at the one I have shown there. Let's go 2 less than or equal to t less than or equal to 4. Okay, and let's think about the starting point again right here, right, and how can I integrate both sides. Okay, so if I start with the starting point, which is di dt is 1 over L times v of t. What I would like to do now is do an integral that ends up with I of t at any time t, not I just at point 2 or just at point 4. So for example, what if I wanted the value of I at 3 seconds? How would I do that? Starting point is t equals what? 2. And the ending point would be t equals 3. So I can get the I3 by just putting limits on the integral, right? Like over here, right? I4 and I2. If I put 3 here, then this would give me the time, I3 instead of I4. So I want you to think general. I'm still starting at 2, but at any time t, what should I put for the top limit? Just t, right? So the starting point's 2. The ending point is any time in between. Okay, so what we'll do is in this interval, let's just go ahead and integrate, but let's leave t as a limit. So I'll integrate from 2 to any time t now of di dt dt. Okay, and on the right, I'll have the integral from 2 to any time t of 1 over L times the voltage, v of t dt. So what you get on the left, right, is I of t evaluated between the two limits from 2 to t. And on the right, I can pull the 1 over L, but I'll get the integral from 2 to t of v of t dt. So let's go ahead and evaluate this with actual numbers in it. See what we get. So on the left, we'll get I of t, right, minus I2. I of t minus I2. Do I know I2?
Yes.
Yeah, it's 36, right? We did the first interval already. So I of t minus I2 is going to be 1 over L. L is 0.500, right? And I need the integral from 2 to t of the voltage. So if I want to get an equation now, I'm not going to use the area of this block, right? In other words, I don't know where the end of the block is, right? It's any time t. I guess I could use the area of the block. But why don't we work the integral? Okay, what is the value of the voltage? Let me ask again. What's the value of the voltage, v of t, in this interval? It's just -9, right? It's the given information here. So I can work the interval, right? So this is -9, okay? I'm going to integrate that, -9 dt. Okay, so this is going to be I of t minus I2. I'll go ahead and put the number in. 36 is going to be equal to 1 over 0.5 is 2. And let's go ahead and evaluate this. What is the integral of -9? Yeah, it's -9t, right? -9t between the two limits, 2 and t. So I'll get I of t. I can move this to the other side. It's going to be 36 plus. Okay, I can, evaluate the limits, factor that out, whatever. I will go ahead and evaluate the limits. Top limit is t minus 9t minus the bottom limit, so minus negative 9 times 2, right? I got a double negative in there. Got to be a little careful. Okay, so at that point, probably would have been good to do what I recommended before. Pull the minus 9 out, right? All right, either way, let's see if we can keep track of the negatives. 36 plus, what's this? 2 times minus 9, minus 18t, minus negative 18 times 2, right? So this could be what? Plus 36. So apparently, I of t is, let's rearrange it, the linear term first, minus 18t plus 36 and 36, 72. By the way, this is an equation of the form what? Y equals mx plus b. Okay, and so this is the equation of that line. Okay, but if anything, this exercise kind of illustrates for me why I don't want to do these problems this way, right? Because if my approach to plotting this was to get the equation in every interval and then plot the equation, it starts to get kind of annoying, right? Because look what this one does. Y equals mx plus b. Well, I can get the m, right? The m is the slope of this thing, minus 18 and 1. And then the b is what? The b is 72. So in this one, right, I'm going to be up here, right, at 72. Where's this one going to be? Right? It's up there somewhere. Okay, so these piecewise lines, having the equation of the piecewise line is not very helpful for me to plot it. It's a lot easier to say, look, it's a line. I know the starting point. I get the end point from the area. I connect the dots, and I'm done. Okay, so when you need the equation, you can get it. In general, not that helpful. Okay. All right, we got a little bit more of circuits. We will pick up where we left off next time.